We continue to discuss chapter 29, section 3, nuclear radioactivity. We're going to discuss radioactive decay. Okay, see, radioactive nuclides are the isotopes, and many of them are unstable. They are not stable. Unstable means a nuclear is going to emit, give off particles or give off energies spontaneously. Okay, and that we call radioactive decay. If a nuclear give off particles, give off energies automatically, the key is automatically. So we call radioactive decay. Usually, the nuclear fission and fusion we call strong nuclear reaction has more energy involved. The decay has less energy. There are totally 6 different decays. And here we're going to study 3 of them. They call alpha decay, beta decay, and gamma decay. Because be careful the symbol. This alpha, this beta, and gamma. So these 3 decay we're going to study. So now first we see the diagram. Suppose this is the nucleus unstable. It's unstable. Okay, so now automatically, spontaneously, unstable one going to decay. Sometimes they're going to have alpha decay and give off alpha particles. This is called alpha particles. 2 proton and 2 neutron. One alpha particle has 2 proton, 2 neutron. And sometimes you're going to say beta decay. Beta decay, you find electrons come out. So now electron is the beta particles. You may think we don't have an electron inside here, right? We only have proton and neutron. What happened is a neutron changed to proton. So neutron has no charge, change to proton, positive charge increase, then you need to have a negative charge. And this electron usually has higher energy. So alpha particle, 2 proton, 2 neutron, has positive charge. And beta decay give you beta particles, which is negative charge. Now the third one we call gamma decay. Gamma decay is just a wave, or you can call photons, right? Okay, the frequency, just like a frequency of X-ray, usually is a little higher, but from inside, nothing change. Nothing change. Not like the alpha decay. You have 2 proton, 2 neutron come out, then nuclear change to another nuclear because number change. This one also, the beta decay, you have 1 neutron change to proton, so the number change, atomic number change, so change from 1 nuclear to another. But this one, the gamma decay, before and after is the same. You just have some energy released. Where high frequency and high energy, we call beta decay. Okay, so again, alpha decay emit alpha particles. Each particle has 2 proton and 2 neutron. Beta decay, electrons emit. Okay, so 1 neutron change to 1 proton. So now the last one is gamma decay. Give off photons, or we can call the EM waves. Okay, gamma ray has both particle nature and wave nature. So now, when decay happens, how we know which one happens? Well, we can use magnetic field. So this cross here, magnetic field go inside. So now, so we can use what we studied when we study chapter 19 and 20. magnetic field. So now alpha particle going to what? Going to change one direction because positive charge inside of magnetic field. Okay, you use the right hand. So the positive charge go to the right. Magnetic field go inside of paper. The force goes up. So alpha particle will go this direction. The negative particles, the gamma particles, because negative will go another direction. Gamma will keep the same direction because gamma doesn't have any charge, no positive, no negative. Okay, so that's a 3 decay, alpha, beta, and gamma. So now, after radioactive decay, when nuclear reduce energy or lose some particles, then become more stable. That's why they decay. That's why decay. Of course, when decay happens, usually we have a big sample, not just one nuclear. We have many, many of them. We can see like trillions of them, or even more. Okay, do you think the trillions of nuclei are going to decay at the same time, just take no time? No. Well, some decay first, some decay later. But in average, they have a speed, how fast decay. Some sample decay very fast, some decay very slow. Okay, so now here we call decay law. It's from experiment. So the delta N is the change, the particle decayed. Okay, then this N here, capital N, is the initial number. Okay, delta T is the time interval, and lambda is the decay constant. Different sample has different constant. Bigger number means decay faster. Okay, so this is called the decay law. So the change of number always decrease, so that's why I have negative sign here. How many particle decays equals the decay constant times the total number, then times delta T. How long for decay? You take a sample like every 30 seconds or every 2 minutes. That's delta T. Longer time, of course, more number decay, more the nuclei decayed. So now this is really a differential equation. You can see that dN and dt. So if we solve it, we need the calculus. So we're not going to do it. And here's the solution. Solution for the decay law. For decay law, we solve this. We got this. So now the n sub O is initial number before decay. Then the number going to decrease. Decrease is when going to change. Going to drop, right? Initially, when time equals 0, you have this many. So then the number going to decrease when time goes on. So this exponential negative lambda. Lambda is the decay constant, and the t here is the time. When time goes on, you can see the number change. Initially, you have n sub O, that's this number. Then the number going to change with time. When time goes on, decrease. So now we have a very important concept we call the half-life. So what is half-life? The half-life is when the initial number reduced to the half. The corresponding time here we call half-life. When the number reduced to the half, from here to there, initial number, half initial, and the time we called half-life. Okay, so now how about the second half-life? Another half-life you think is totally decayed, right? No, it's not. Another half-life, okay, see, this time and that time the same time, you're going to change half of this decade. You have 1/4 left. You can have a third half-life, fourth half-life, forever. So half-life is when initial number uh, change to decay 50%. Is a time period for half of the sample decay. Half a sample decay or 50% decay. Okay, so mathematically we can find it. We say when this number here equals half of the initial number, if n equals half of n sub o, then the time we call what? Half-life. Okay, so we plug in. So when n equals half of n sub o, the t is half-life. So we say n equals half of n equals n times e to the power lambda and t half-life. This half-life. So then we can solve because both sides have n sub o. You can divide by that number both sides. You're going to have 1/2 equals e minus lambda and half-life. Then you take natural log both sides, and you can solve for the half-life. This is how you can find. Of course, we assume we already know the decay constant. So half-life equals ln 2 divided by decay constant. So in the lab, we can measure the decay constant. If we find decay constant, we can find half-life. The half-life can be very short or very long, like radium. So radium, this is the upper decay. Radium change to radon. You see the number change. 2 proton out, 2 neutron out. You see the bottom number reduced 2, the top reduced 4. 2 protons, 2 neutrons. And this half-life equals 1600 years of decay. Carbon-14. Carbon-14. So carbon-14, what happened is the 1 neutron changed to 1 proton. So the total number is still same. 14 and 14. Because same the nucleons. 1 neutron changed to proton. But the bottom number changed. So carbon changed to nitrogen. So 1 changed to another. This also 1 changed to another of decay and beta decay. And some decay, the half-life can be very short. And this is like what we have, 2.57 minutes. So you can measure it. Okay, so next I want to give you a demonstration. See how this works. Okay, here's our lab. Okay, we're gonna see a few photos first. Okay, this one. This is our sample, and inside we have the decay sample. What we have is the cesium and barium. Okay, 137. We call isotope generator. So now this half-life is about 2.5 minutes, about 150 seconds, 160 seconds. Okay, so we need to prepare a sample. So we use this special solution. Then drop. We open this side and that side. Okay, so we drop the liquid inside and wash out some sample. Then use small tray. Small tray hold it. Okay, so next, here's the Geiger counter. We use this one measure signal. So we put the sample underneath right here. Then we turn on the power. This is the interface. Then connect to computer and we use the software. And this number tell you the decay, how much decay. Okay, so let's say, yeah, this you can see better. So here's data. So we take every 30 seconds and totally 30 data. So the first 30 seconds, we measured 5,125 decay. Second 30 seconds, you find 4480. See the number drop, then 4,000, 3,500, 3,000, 2,700, 2,400. So every second you take data, but the number decrease, 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 decrease. Okay, so here's the voltage. We need to use 900 volt for the Geiger counter. Okay, so now let me give you a demonstration. Okay, let's say this is one. We're going to take data, and you can hear sound. Let me make the sound a little bigger. Okay, so we're going to take data, Again, I have to use one hand hold my cell phone, so it's not very stable. So, okay, 30 seconds each time. Okay, so the first data is 13 seconds, 14 seconds, 15 seconds. And we're going to take 30 data. Okay, 30 seconds. So now you have first data. See, 5,125. That's first data in first 30 seconds. Then continue with another 30 seconds. You're going to have second data. And you can see the number drop, drop, drop because the decay. So now we almost have the second one. Okay, second one. Second one, you have 4,479. Well, let's see another one. You will close this one. We see this one. We're going to see more data. See, still going on, See, we already have so many data. 1, 2, sorry, 3, 4, 5. You see the number decrease, decrease. We already passed first half-life, right? So initially I have 5,100 something, and this one here is almost half of initial. Sorry, that's me. Okay, that's about half of first one. So now every time I have 30 seconds, 60 seconds, 90 seconds, 120. So you can figure out half-life. Okay. So now let me see our data. And online 3 for students. Okay, these 3 lab combined. Okay, we're gonna see the last part. Okay, here's data. See, that's first data 5,000 something, and every 30 seconds you take another data. Every 30 seconds. So now see, this one almost equals half of the initial. So here's the total time. We start from 0. After 30 seconds, 60, 90, 120. See, 150 seconds. The number dropped to the half. So the half-life equals about 150 seconds. That's 2.5 minutes. So now if you wait another, we continue, another half-life. Okay, you see, okay, so now when this number dropped to 50%, 26 something, 13 something. Okay, so now you count time again. So that's another 150 seconds. So first half-life, second half-life, then you continue third half-life. Well, this number a little off. So now it will be a little longer. Okay, so you can measure this. You can measure the half-life, which is when the number drop to half. Drop to the half, take 150 seconds, then drop this one, drop second one, drop half, another 150 seconds, so on. Of course, if we just counting the numbers, not very accurate. This is the lab I gave long time ago. This for physics class. Anybody know him? Okay. So anyway, so you can input all the data. This is 30 there. You see the dots on the blue color one, 30 of them. Okay. So then you feed this curve. Use a software. So you can figure out the decay constant. That is the lambda. After you find the lambda, you can find half-life. Okay, so that's how we measured, but we don't have this lab this semester. Okay, so now that's how you do it. You use that curve we just discussed. You can figure out the decay constant. Then ln 2 divided by constant give you half-life. This will have much accurate data. Okay. So anyway, so that's radioactive decay, and very important concept is the half-life decay law. Okay, so we can discuss just a little more detail. So we have many applications like dating of the fossils. Okay. You see the carbon 14. This carbon 14. Carbon 14 has half-life almost equals 6,000 years. 6,000 years. Okay. So when animal died, well, they're not eating anymore. Okay. So then in the bone of the animal, the decay start. So every 5,700 years, the carbon 14 going to reduce to half. Then another 5,700 years reduce to half of half. Okay, so if you can carefully measure the carbon 14 left in the fossils, then you can estimate when this animal died. So that's called the dating. So simply speaking, understand half-life. So if initially you have 10 grams of sample, after first half-life, 5 grams left, from 10 to 5. So now after second half-life, 2.5 grams left. After third half-life, totally is like 4,800 years, 1.25 grams left. Okay, but you can only dating certain time because finally the decay become so small number, so you cannot measure, at least not very accurate. So now we're going to spend a few minutes, give you a few important, give you this equation for the 3 decay, alpha decay. Okay, usually before we call the parents nuclear, after we call daughter nuclear. See, this is alpha decay. You see the parent, so the Z number are going to reduce to 2. A number reduce 4. That means you have one alpha particle come out. So, okay, 2 and 4. Okay, here's the example. So alpha decay always give you these alpha particles, which is really nuclear of the helium. Okay, now the beta decay. You're going to say the total number of the A keeps the same, but the Z number increase 1. So the parents and the daughter, the A is the same, but Z increase. Then at the same time, you have one negative charge come out. This is a beta decay. Well, neutrinos is another particle from the beta decay. We are not going to discuss. Okay, now the last one is the gamma. See the gamma before and after, the parents and daughter is the same thing. Same Z, same A. But what happened? We have star here. Before you have more energy, after a little less, because gamma ray come out. you can call photon, you can call the ray, or you can call wave. So that's three different decay. Well, this end of the chapter 29. Thank you.